Hi everyone. For Alex, okay. Hi Alex. Happy birthday. Very excited to be here and very happy that this all thing is taking place and so many people are here. Okay, so going back to 10 years ago, it was Alex's 60th birthday. I wasn't part of this crowd at all. I wasn't, invited to the to the party. But I already knew that I want to be in the party, and Tali said, why don't you come with me? So I came with Tali to the dinner reception. It's like anyway, and then I think the following year they had this special year here in the Midrasha on high-dimensional expansion, and it was just amazing. It blew my mind. It was really one of maybe the most fantastic year I had. And Alex, and not only him, but his spirit and his crowd, a lot of you were so welcoming, happy to explain things over and over, and just very open to talk to people about questions that maybe are not interesting for you, but just, be generous with explaining. So that was really a fantastic experience. At the end of the year, it was over, and I was like, oh, what will I do now? So I realized I have to do a pilgrimage and come to Jerusalem to talk to Alex, and he was happy to see me, I hope, and we worked every week. I came every week to Jerusalem, and we started to talk, and more people joined, Shachar Moses, and Ron Livne, and then Shai Evra, and we were talking for a long time. It took us to do this work. And here is one picture from this collaboration. So this is Ron Livne. I was when I started coming to Alex's office, I was quite shocked to see his very humble office. They don't have sofas there. They have these wooden chairs. And at some point, I felt comfortable enough to say something about that. And he told me, no, this is a luxury, And he proved it to me that on the bottom of this wooden chair, you have this is like from the early 50s. It says luxury tax, 1 lira. Okay, so this is a true to life picture. Anyway, okay, so all right, I'll talk about expanders now. Alex kept iterating that it's important to have a kenes limudi, so educational. So I decided to spend most of the talk talking about one of Alex's works that I find the most amazing, and try to explain it to some level. So let's see if I manage. So I start to say that Lubotzky, Philip, Sarnak expanders, of course, they're amazing and very celebrated, coming from quotients of the infinite tree. And the claim to fame for them was that they have the Ramanujan property. But from different perspectives, they're not as good even as just any old random graph. Like lossless expansion or other properties that random graph has. And these graphs don't seem to have. But then the higher dimensional analog of the LPS expanders is this amazing work of Alex with Beth Samuels and Uzi Vishna, the LSV expanders, which are the same as the LPS, except instead of taking the infinite tree, you take quotients of the higher dimensional analog, which is the Bruhat Tits building, whatever that means. So to me, of course, this didn't mean anything at the time, but very interestingly about this is that this is absolutely better than random. The minute you see it, you see that random cannot even begin to compete. And one of the most amazing properties is that it's a simplicial complex, so it's like a graph, but you also have triangles and higher dimensional faces. And it has a feature that, on one hand, a lot of the faces are overlapping, so a lot of the triangles meet each other on edges, but on the other hand, it's expanding. And when you try to select a simplicial complex at random, you will never have this property. So this is something else, and you probably need a group structure to have such a thing. In fact, we don't know of any construction that doesn't come from groups. Fodor. So I said the word groups. Okay. Slowly today, you know, we're moving away from. Okay, so one way to think about how special these complexes are is that they have a feature which we will call local to global. Different areas of math use this term to refer to completely different things. So here it will be maybe different than what you're used to. I'll say exactly. This is a feature that we don't have in one-dimensional expanders. The most prominent and well-understood kind of manifestation of this is the trickle-down theorem of Ishar-Oppenheim that goes back to Zhuk and to, this is really Garland's method. He was able to understand what happens at the links, and from there to deduce something globally on the entire complex. So for me, local will be something at the level of links. Always our complexes will be bounded degree, so the link is something very small, whereas the global complex can have size going to infinity or even infinite in Garland's case. So this is spectral expansion, and this is not what I'm going to talk about. It has the local to global feature, but I want to talk about the other kind of expansion. So in the earlier days of this area, we said graph expansion has many different forms. You can talk about random walks, you can talk about bottlenecks in a graph, and so on. And each one of them generalizes differently to higher dimensions. But really, as time went by, we realized there's actually really two important different ways of thinking about expansion in higher dimensions. One of them is the spectral, and the other is this cohomological notion, which I want to talk about it as if it's a property testing or a local testing notion, because that's the way that's easiest for me to understand it. And the second way has always been more mysterious, so that's why I want to devote some time to it. So I will talk about it in three ways. The main thing I want to talk about is coboundary and cocycle expansion and this work of Kaufman, Kazhdan, and Lubotzky. This is from around 2015, I think. And it was, for me, I think it still is probably the most amazing work in this area, because it proves something from local to global that how else would you, it's like a new technique in some way, and hard to imagine a different way of proving this thing in retrospect. And then I want to show how really our work with Alex on locally testable codes, there was a question in computer science about good locally testable codes that Pavel was referring to the other day when he talked about bad ones. But anyway, we had this work on them, and the entire work is really modeled after this proof. So I want to spend some time on this proof and then show how our work is really analogous to that. And in the last part, I will talk about a different problem called agreement testing or direct product testing, that I was working on it somewhat separately from these other works, and I didn't even think it's related. But as time went by, it turned out that underneath this, again, this coboundary expansion is very important. So to mention that. So the talk will have three parts. This is the main part, and then these other two parts towards the end, or half. Okay, so I want to talk about cocycle and coboundary expansion. This is a notion that was introduced by Nati Liniel and Roy Meshulam, and independently by Gromov. And usually when we describe what it is, we start with the notion on level 0, so functions on the vertices, and then we show, oh, you know, this is exactly edge expansion. And now let's syntactically just see how this definition upgrades when you move to level 1, level 2, level 3. And that's okay, so I will describe the level 0, but it turns out a bit boring. And then I will describe the level 1, which to me that's the main thing. So stay tuned. So for level 0, you just have a function on the vertices, f, and then there is this operator delta. I think I wrote it over here. So delta takes functions from the vertices to functions on the edges. By just on every edge, it says, let's add the values on the two endpoints. So delta f at the edge uv is just the sum of the endpoints. So what does it mean for delta f to be 0? It just means that on every edge you see the two endpoints are the same, mod 2. Right? So it means that f, the set of ones, there is no edge leaving this set of ones, because if there was an edge with 1 here and 0 here, delta f would be 1 on this edge. So delta f being 0 means there is no boundary, so your f is constant on an entire connected component, or maybe 2 of them, or all of them. So that's what it means to have delta f being 0. And now we can ask, what is an f where delta f is almost 0? So suppose someone tells you f is not exactly inside ker delta, but it's close. So maybe a few of the edges have a non-zero delta, but almost all of them it's 0. So what does it mean about f? Does it mean that f is close to being delta f is almost 0, meaning almost all the edges are 0. Does it mean that f is close to being one of these good functions in ker delta? Okay. So what do you think?
Depends on the graph.
Depends on the graph. Right. If the graph is a very bad expander, imagine like 2 cliques with one edge connecting them. Then I can have f that is 1 on an entire clique, 0 on the other clique, and only one edge will light up. Right? So it's clear, this graph, we know it's a bad expander. It has this bottleneck. And this is shown here. It satisfies that delta f is almost 0. Almost all the edges are 0. But it's not close to being anything in ker delta. Okay, so and this is equivalent, this definition, when a graph satisfies this equivalence, it's exactly saying that it's an edge expander. So that's the definition of an edge expander from this homological language with using this delta operator. It's called the coboundary operator. Okay, so far, as I said, I don't think it's very interesting, but now I want to move to dimension 1. So now my f is no longer a function on the vertices. My f is a chain, a one chain, so it gives a label of 0 or 1 to every edge. And for starters, it's good to imagine that my complex is the complete complex. So imagine that my complex has all edges and all triangles, just for starters. So my f labels some of the edges with 0 and some of the edges with 1. Now what is the delta operator applied on f? It moves me from a function on the edges, so here I guess it denoted it x1, these are the edges, and it takes me to a function on the triangles. How does it work? For every triangle UVW, I need to add the value of f on the 3 edges, UV, VW, and WV. Okay, so in the case of the complete complex, you can think about what does it mean for delta f to be 0. Okay, so for every triangle, you get a 0. So look, if you have a triangle, maybe imagine I put here another edge. What does it mean that the triangle always sees an even number of edges? Well, here we see one example. Imagine that f is just 1s on all the edges in the cut. Okay, so I'm sorry that here I labeled 1s and 0 on the vertices, but our f now is a function of the edges. And if f is just highlighting all the edges in the cut, then for every 3 points that I choose, either they cross the cut and then 2 edges are 1 and 1 edge is 0, or they're all 3 inside one side of the cut and then all edges are 0. So every f that indicates a cut satisfies delta f equals 0. And in fact, it's if and only if in the complete complex. There are other situations where the complex is not the complete complex, so not all the triangles are here and not all the edges are here. And then it could be that other kinds of functions satisfy are inside ker delta, not only cuts. But for now, it doesn't matter. Either it's a cut or it's something else, which we call a cocycle. So we're now kind of interested in the set ker delta, all the functions on the edges that are 0 when you move them to the triangles. This is our kind of special interest right now. And now I ask myself, okay, what happens if I know that delta f is not 0? So there are some triangles that are 1, but almost all the triangles are 0. can I deduce that f is close to being inside this special set? Okay, so it's analogous to above. Even here we saw that it depends on the graph. Sometimes, and it's easy to see once you understand its expansion, it's easy to see examples of a graph where this doesn't hold. But here it's already not so easy to even get a feeling for what this is. Is it true for every graph that if you're almost zero, then you're close to something that's actually zero? Okay, the answer is no, but it's harder for me to draw a picture of that. I'm not going to do it. But for the case of the complete complex, it's true. So this is what I'm now saying, and it's actually there's a paper that proves this. It's not a priori trivial thing. If you have a function on the edges, so think of it, you just have a graph. The function on the edges tells you which edges are there, so it's a graph. And you know that for every 3 points, the number of edges you will see is even. Actually, you don't know it for every 3 points, you know it for almost every 3 points. It means that this graph is close to being something very special. What is this something very special? A biclic. So there you can split the vertices into 2 parts, and all the edges just go between the 2 parts. Okay, so this is a theorem. It means it's a stability theorem. It says if this happens for almost all the triangles, the graph is not a biclic, but it's close to being something like that.
You change a very small proportion of the edges,
and it becomes one. You can fix your f. So it's kind of a nice situation where if f passes almost all of the local checks, these triangle checks, it means it can be fixed, and kind of you can change it and make it perfectly in Kerr delta. Okay. So in the more general situation, for complexes that are not all the complete complex, Kerr delta is a bit larger. It's not only the cuts, it's also the cocycles. But even in the case of this complete complex, in computer science, there's a whole area of property testing. And you look at the graphs, and you want to know various properties of the graphs. Like, is it a biclic, for example? That's a property. And there is a paper by Goldreich et al. That actually proved that doing this triangle test is a good property tester for being a biclic. So it's not a priori immediate at all. And this kind of connection between property testing and coboundary expansion was first made in a paper by Kaufman and Lubotzky. They kind of discovered that this definition is actually a property testing question. And I remember Alex was telling me when he was visiting Boston, I think, in 2013, and kind of discovered this and was so happy about it. And I thought that's very cool, but I didn't understand yet how important it will be for me. I thought it's like curiosity, it's nice, okay. So anyway, they had this insight already back then. And I thought I would, since it's like educational, I'll give you an exercise. I want to demonstrate something about the area of property testing, and that it's not a trivial thing. So I don't know if this will demonstrate it or not. But there is this well-known graph. It's the projective plane incidence graph between points in the projective plane and lines in the projective plane. You think of the plane, points and lines. On one side you put a vertex for every line, on the other side a vertex for every point, and you put an edge if they're incident, if the point is in the line. It's a graph. Now you use this as your underlying world, and you think of a one chain. A one chain chooses some of these edges, not all of them. So it labels the edges by zeros and ones. So you're given this one chain as an input, and you want to know, did this one chain come from choosing a bunch of vertices on either side and putting only the edges that cross between this biclic? Okay, this is the question. Maybe it's a weird question, but this is the question. So can you think about a local test for this thing? So I'm giving you this one chain, and I'm asking you, is it equal to something that comes from choosing 2 vertices and just looking at the induced graph? Is it close to an induced biclic? Now, in this graph, this points versus lines graph, we don't have any triangles, right? Because it's bipartite. So you cannot do the triangle test. So what would you do? can you think of a local test? So a local test is to look at only a small part of this graph and check. And then I want to know if it's an induced by click. If it's, yeah, if it's... Take a sample, like maybe look at a few edges, or maybe look at a few vertices and all the edges on them, and see if in this sample you can explain what you see by a by-click. Yeah, that would probably work. But I have an even better...
You want to really check if it's a cut.
Yeah, I want to check if it's a cut.
Like a sum of everything or something, like if you really want to check if this function gives you a cut.
Yeah, you can look at everything and look at all possible cuts and see if one of them work, but you want to look at a very small part of the graph. Yeah. Sorry? Right. Okay, good. So in this graph, I mean, those who know, and the other ones you wouldn't know. There are very short cycles. In fact, there's these hexagons. Because between every 2 points there's a line. So anyway, there is a very short 6 cycle. And you can look at this 6 cycle, and because it's an even bipartite thing, you can see it's very similar to what Ehud said, but it's like the shortest possible, smallest possible graph where it makes sense to check. And you can check if your function there looks like a bipartite thing. And in fact, you can prove that this is a good test. What does it mean? If the one chain satisfies almost all the hexagons, then it's close to being an induced cut. But you need to prove it. I mean, it's not obvious. So this is, we leave it as an exercise. Okay. All right, so to summarize this part, I want to say that we always, this is general in property testing, we have these 2 measures of closeness to our special set Kerr delta. In property testing, we call this set capital P. It's like our property. And there's a nice way to define it, like being an induced by-click or something like that. Here, the nice way is it's the kernel of the delta operator. And there's 2 ways to measure how close you are to this set. One is to see, you are a function. You're, on every edge you say 0 or 1. How many values of this function do you need to change to enter this property? That's like the most natural measure of distance from a set. But the other measure is the testing measure. It says, okay, I have these local checks, and I want to know how many of these local checks accept or reject. Okay, so this is a much easier measure to actually measure. And this is the more natural thing we really want to know. And property testing tries to relate between the 2. And combinatorial expansion is exactly when these 2 things are equivalent. So you can know your distance to Kerr delta by knowing how many triangles reject. Okay, so that's kind of the heart of it. If few triangles reject, you can fix it. And the question that was open at the time, and Alex and et al. Were interested, is can there be a complex? Not like the complete complex we know has this property. Can there be a complex with much, much fewer triangles, so bounded degree, like in expander graphs? Expander graphs imitate the complete graph in their connectivity behaviors. Now we want something analogous. We want to have something that imitates the complete complex in this behavior, but it is sparse. There's only a constant number of edges touching every vertex, a constant number of triangles touching every vertex. Okay, and I think, I don't know, maybe Alex can say, but I think he always carried this LSV construction. He thought it was, he already knew that it's something special, and he was carrying it and trying to find ways to demonstrate this specialness, and then this seemed to be one way, and indeed that's what they proved. So as I said, any kind of random construction that we can think of never will have this property for bounded degree. In fact, in Lineal and Meshulam's paper, they showed that if the graph has complete full skeleton, so all the edges, and then you select some of the triangles at random, maybe logarithmic density, then you have this property. Okay, so why focus on this kind of strange-looking property? So firstly, I think one big push was there was this work of Gromov on something called topological overlap. And he proved that if you have a coboundary expander, you will have this property. So they wanted to construct one with constant sparseness. Later, it was discovered that it's related to covers of the graph, and whether if you have something that's almost a cover but violates some of the triangles, can you fix it to be an actual exact cover? And this relates to group stability. And as I already hinted in the beginning, this also relates to agreement tests that come from questions coming from PCPs. We'll see that towards the end. Okay, so I already said that we know the complete complex is a coboundary expander. And the way you prove it, in hindsight, you can call it the cones method. This is a general method in, I guess, in topology. I'm not going to get into it, but it's kind of the proof builds the, you have your function f. It satisfies almost all the tests. You want to know if it's actually close to something that is a cut. So you build the cut, kind of using these cones. That's a natural way to prove things. But in other cases, you cannot apply the cones method. And this is this beautiful local to global theorem. Given a simplicial complex X, one kind of interesting thing, the proof needs the complex to be three-dimensional. So what does that mean? Clearly, the complex needs to have vertices, edges, and triangles, because you're going to have a function on the edges and you're going to map it to triangles. But somehow, we need the complex to also have one level above the triangles, what we call pyramids. Ken?
When you say the complete complex is coboundary expander, like what is the constant?
It's actually 1. It's actually a bit above 1, which is crazy. What I mean is, remember we had these two measures of distance? Coboundary expansion means that the fraction of triangles that reject gives you a lower bound to your distance, and there's a constant that relates the two, and the constant is 1, when you normalize correctly.
It depends on the degree of the,
No.
On the dimension, there's a tiny dependence, like maybe it's like n divided by n minus the dimension. I don't remember, but something like that. So it's even a bit bigger than 1. And the proof is like 3 lines. It's very simple. Once you know it. Like always. Okay, going back. So the theorem is this. You have okay, the theorem here is general. It's for any complex that satisfies certain things. But really underlying it, we think of the LSV complex, this quotient of the building where the links have constant size, and the whole complex, has size that grows to infinity. Okay, so the theorem, the local to global theorem, is you start with an X, and it has some properties. What are the 2 properties that it needs? You need that all the links. So for every vertex, you just look at the complex restricted to neighbors of this vertex. I have a picture, but never mind. If all the links themselves are coboundary expanders, then the entire complex is also a cocycle expander. In this complex, we don't know anymore if the cohomology is 0 or not. So we can just ignore it and think that I wrote here coboundary expander. For the purpose of the proof, it doesn't care if there is some cohomology or not. From the property testing point of view, what you're doing is you're saying, suppose you prove this theorem. What it means is that now if you have some one chain, so some function on the edges, that satisfies almost all the triangles, you can fix it to something that satisfies all the triangles. And now you don't care if this, so this something is by definition a cocycle. Whether it has to be a coboundary or not, it's not important. So if you've never heard about these things, just ignore it, doesn't matter. Okay, so one thing I maybe forgot to write is you also need the graph to underlying to be a spectral, just a normal expander, just the edges. So you need the underlying graph to be an expander and all the links to be coboundary expanders, and then you get a cocycle expansion. This is the local to global. If you have locally some kind of testability, local testability property, you get it globally. And I think it's interesting that we don't know how to prove it, this theorem, without having these three-dimensional faces above. So,
Question.
yeah.
So when you talk about links, whose links are they? What dimensional sequence?
Yeah, thanks. Okay, so here I have a picture. No, okay. Yeah, no. I'm sorry. I thought I have a picture, but I guess I erased it. Okay, so thank you. So just to be sure, what are links, right? So, I mean, I'm sure you know that, but when I have an edge and I have a three-dimensional complex, it means that this edge participates in triangles, and it also participates in pyramids. So there's also, like tetrahedra. Thank you, tetrahedra. So this is an edge UV. The link of UV is really you put vertices for all the neighbors, and you put edges whenever UV together with these two guys make a three-face, a tetrahedron. And so the link here is a graph. This is the link of an edge. A link of a vertex is, again, you look at all the neighbors, and you put edges when they participate in a triangle, and you put a triangle in the link whenever they together participate in a three-face. So here we're talking about both the links of vertices and the links of edges. And there is a generalization. Very sorry about this. Did I have it twice? Yeah, sorry. Okay, so there's a generalization of this theorem for all dimensional complexes X by Shai-Avra and Tali Kaufman. And that proof is even more sophisticated, and there you need links in all dimensions. But we will only focus on expansion of one chains. Here is my picture. So this is the link. So the link of this vertex here is just this 5 cycle in this picture. Okay. Okay, so I want to give a proof sketch. This is, I think, okay, it captures kind of the main idea. I'm not going to do all the details, but let me try to do it. And how are we doing? So we. Okay. Thanks. Okay, so this is a local to global thing. So we start with a one chain, F. So F is on the edges, and delta F is on the triangles. And we are given the fact that delta F is almost 0. So most triangles are even. So what can you do with F? You really want to show that it's close to some other F where delta of the other F is actually 0. You want to correct it. You want to change it until it satisfies all the triangle tests. So you run this greedy algorithm. This is like, what else can you do? And in this algorithm, you say, oh, I look at an edge. Now I think I have a picture. Yeah. Okay, I have a picture. You look at an edge, and its value, F gives it a 0 or 1, I don't know. But it participates in some triangles. And if this triangle sees a 1 here and a 1 here, then this triangle wants this edge to be 0. That triangle, maybe it wants this edge to be 1. So every triangle has a different desire for this edge. And the edge looks at all the triangles, and it says, oh, if I can flip my value and improve, like reduce the number of unhappy triangles, I will do it. So that's one thing you do. And the other thing is with the vertices. So I guess we also have a vertex here. So this vertex, it is like in charge of all of the edges going out of it. And look at these two edges, okay? Here is a triangle where these two edges participate. So these two edges, if it says 1, 1, they want this edge to be 0. But maybe it's not 0, maybe it's 1. And these two edges, maybe they want this edge to be 1. So basically, whatever all these edges, the value of these edges here, it dictates exactly what they want on the link. The edges in red here are the edges of the link of this vertex. Okay, so the value on the incident edges kind of says, here's what I want the red part to be. And maybe it's good and maybe it's not. So this vertex looks at the edges near it and says, oh, maybe I can change 1 or 2 or all of the bits here to fit better with what I see on the link. And if I can do that, I'll do it because I will have reduced the delta f. Okay, so that's the local moves. You have a local move for a vertex and a local move for an edge. And these are all local because you think of the complex as bounded degree so that the entire complex is huge, but what you're changing at every step is a constant number of things.
Is it?
Yeah.
The function is on edges.
Yeah.
If you can change the value on an edge, you can make it 0.
If you can change the value of an edge, you need to make the triangle 0.
No, you can change f to be the 0 function.
Right.
He wants local
directions. Yeah, so you don't want many changes.
Okay.
If f is like almost all ones and you make it 0, you changed f too much.
Okay.
Our goal is to say, f can be half-half, delta f can be almost 0, so we want to change f proportionally to this, if this is an epsilon, and make delta f exactly 0.
But do you see the algorithm out? Well, you see that you only want 2 steps.
Yeah, we'll see in a minute.
Okay.
But the second thing is free. The first change costs you, and the second thing you can do for free.
This one?
Yeah.
No, neither. What do you mean? No.
The price is how many edges you change. That's
So if you ask about your distance from boundaries, then you can always change everything touching the vertex.
You want to say that if you
No, no,
close
no.
it, you are close to establish almost everything, there will be few moves and you'll get to it.
Yeah, but she's not flipping the whole
No, no.
star.
I'm not changing the red guys. Only the edges touching my vertex.
Yeah.
So it costs me. So if I change this 1 to a 0, I'm measuring how many changes to f have I made. So I made 1 change. It's costing me 1.
If you change the star of edges touching the vertex, you actually don't change delta.
Yes, she's not flipping the whole star. She's flipping the subset of the star.
I am changing delta f. If this was a 1, okay, if this red edge was a 1, so delta f on this triangle was now 1 plus 1 plus 1. And I changed this edge now to 0, suddenly this triangle became a 0. So I'm improving delta f. Basically, this algorithm is saying, make any local move you can to improve, to decrease delta f. That's what you're doing. Huh?
The confusion was because it looked like you are flipping the whole edges of the star. You're not doing that. You're flipping only the edges in the star that you want to flip.
Yeah, I don't know. Okay, if that was the confusion.
I think so.
But that's true, correct. Okay. Okay, and repeat, right? So you're just greedy, you just keep doing it until you cannot make any move that improves your situation.
But you go to any place, or you try to do it for the best vertex or the best local place you pick the first, any local place to make an improvement, or you pick the...
Yeah, this is like not doing anything clever. Whenever you can make an improvement, you do it, and you do it all over the place. And you see that every time you make a flip, you kind of went farther from f, but in return, you got delta f to be smaller. And since the graph is constant degree, these two things it's okay to compare between them. And you basically see that as delta f decreases, the distance from f increased, but since this started out to be a small epsilon, you didn't move too far away from f.
You move the distance 1 per 1 to the
Yeah, well here, in the link of a vertex, maybe you change a few edges at a time, but it's only a constant, because it's a constant degree. Okay, so this is the greedy algorithm. And we have this algorithm all over the place, like in Spielman's expander codes, in the Sipser-Spielman, the way they decode a code word in an expander code is exactly the same. You have these checks, and you want to satisfy as many checks as you can, and you flip if you can.
But you need both types.
Here you need both types. And when you do the Evra-Kaufman of degree D, you need D different types. Okay. Okay. Weird. Repeat and repeat. Okay, and see, I had some technological problem, that's why I drew it on the board. Okay, these are the two types of things moves we do. And what happens in the end? You get stuck. When you're stuck, we call this f locally minimal. Means that locally there's nothing better you can do. So it's a locally minimal f. Now we want to analyze what does a locally minimal f look like. So we'll say that a triangle UVW is active if delta f is still non-zero there. Okay? And that's the sum along the three edges. Okay, so if delta f is 0, we are happy, right? We are done. So we really need to focus. And the reason we are happy, like we said, is because we didn't move too far away from f, so we found some other f that is actually a cocycle. So now I changed the notation. F is no longer the initial f, it's already the output of the algorithm. Okay, so now we have this f, and it's non-zero. I want to prove that it actually has large weight. It cannot have weight epsilon. It must actually be a large thing. Okay, and that's something you see in all these expansion analyses. A set in an expander that has certain properties must be very large. That's the kind of argument we will make. With respect to? No, like an absolute constant large.
You want to show that you're in case 1. So
you really think that if you start with delta f very small, you will end up here. And this is like the case you're never going to get to. If you're not 0, you must have been like at least 1% large. Okay. So what is the key fact that is used by the proof? It's the fact that when you look at the triangles that are active, okay, this is delta f. It indicates the active triangles. Then delta of this, what is delta of a function on the triangles? I didn't define it. It's you move to the faces one dimension above. These are the tetrahedra. And you sum, so you have like a three-face. You sum over all the 4 triangles. Okay, so it's easy to check, and it's kind of well-known. Always, delta is always orchestrated this way. That delta, these are different operators. This is from edges to triangles, and this is from triangles to tetrahedra. Delta is 0. What does it mean? For every three-face, which is 4 vertices, the number of active triangles must be even. Okay, so if you have one active triangle, there must be another active triangle. Okay, so that's the key. Now the proof, what it does, it's going to think about a random walk from triangle to triangle. You start at a triangle, maybe it participates in several three faces, you move to one of them at random. If this initial triangle is active, for each one of these three faces, there must be another active triangle out there. Right? So from one active triangle, we already deduce a bunch of them. That's already like a good start. So you think of it as a random walk. You start from an active triangle, you move to another, then you do the same. You move to another, and another, and another, and you're supposed to kind of expand over the whole graph, and that's why the set of active triangles is huge. So, but this is not exactly as easy as that. What you're doing is you're moving from triangle up to a three-face and back down, so it's an up-down walk. And we know that this up-down walk stays inside the active set with some probability, maybe probability half or something like that. And now you want to use this fact that in an expander, if a random walk stays inside a set too much, then the set must be large. That's kind of a basic property of an expander. You cannot stay stuck inside a small set. But somehow the numbers don't work in our favor here. And the reason is exactly these two examples, I guess. Let's remember, okay, I don't remember what my slides have, so let's do. So let's see. The up-down walk, it is expanding, but there are some sets where it stays too much. So what are those? One is the set of all triangles that touch an edge. Okay, I guess this corresponds to this to this set, right? If you think of inside your whole complex, just think of the set of all triangles that touch this edge. This set of triangles, when you do this up-down walk, so you move from this triangle to some three-face, so maybe it's like this for example, this three-face, these four, and then you go back down. Well, you might go to a three-face like this, which is outside of your set, but with good probability you'll go to either this triangle or that triangle. So there's like probability half of staying inside this set of triangles touching this edge. So it doesn't satisfy the property we want that you always exit the set. And another problematic set is the set of all triangles that touch a vertex. Okay. Also here, when you go up and then back down, with good probability you'll actually you'll remain with this vertex. There's only probability 1/4 of moving to a triangle that's away. Okay. So what is the crux of the analysis? You need to use the fact that your complex had coboundary expansion on every link. We didn't use it yet, right? Because it has coboundary expansion on every link, it guarantees that the collection of active triangles can never have a strong correlation with these bad sets. Okay, so there are these bad sets. These are sets where the random walk stays stuck. And because of coboundary expansion, you're not really ever going to see such a collection of active triangles in a locally in a function that came from this algorithm. And why is that? So let's see what I have here. I guess no, I just have this picture. So let's see. Okay, firstly, let's look at the collection of triangles that, so think of this edge, and you have all these triangles that touch this edge. If too many triangles are active on this edge, like more than half, then you can flip the value of this edge and reduce the number of active triangles, because then all the ones that were active become happy, and all the ones that were happy become active. So you made progress. So it means that around every edge, no more than half the triangles are active. And what this means, if you imagine, because of the coboundary expansion, around every edge, the collection of three faces, this forms a graph. And in this graph, no matter, whenever you have a cut, there's going to be many edges crossing the cut. And this corresponds to four faces that will see an odd number of triangles. See one triangle from the set of ones and another triangle from the set of zeros, and will force some active triangles outside this set. So what I said now is this. If only less than half of the triangles here are active, there must be some active triangles outside the set of outside this star. So this is given to us by the coboundary expansion of the link of the edge. Now, similarly for the link of the vertex. So what's going on here with the link of the vertex? We have some number of active triangles. Okay, so remember, the value of f on the edges touching this vertex makes a demand on what it wants to see out here in the red. Okay, and now if there are no or almost no active triangles on the red, it means that from the point of view of the red, almost all the triangles here, so triangles like this, are happy. Okay, but we know that this graph, actually it's a two-dimensional complex, this red part, itself it's a coboundary expansion. So what expander? So what does it mean that almost all the triangles here are happy? It means that there is a way to see this function as a cut. There is a way to write the function on these edges as a cut, and that means that there is a way to kind of meet this cut from below and change the value of these edges to exactly fit what is written up here. The upshot of this is that whenever you have many active triangles touching V, there must also be many active triangles away from V. Okay, so the coboundary expansion tells you that the set of active triangles always pushes away from stars. It pushes away from vertices, and it pushes away from edges. And you need this kind of local property in combination with the spectral expansion, and the argument goes through. Okay, questions, because this was...
So are there any other sticky sets other than
Great, thanks. So good question. I just laid it on you that these are the sticky sets, and Elazar is asking, are there any more? And the answer is there aren't. Once you are able to move from a triangle to a triangle that is disjoint from it, so it doesn't share any vertex or edge, this walk is already a great expander. Like the expansion, the second largest eigenvalue is close to 0. So in that, when you've reached that, you're already happy. You know you can never get stuck. So these are really the two sticky sets. And when you're in dimension D, you have sticky sets in all dimensions. And you slowly kind of peel them off. Okay, so to summarize again, we had this like random walk argument that is, you see it many times. But here, you needed some more information to show you how you cannot get stuck in some local obstructions. Okay. So this is all I have to say about this proof. I mean, it kind of has this beautiful combination of the local part, and the spectral random walk kind of allows you to lift the local testability, which is called coboundary expansion, to global local testability, which is called cocycle expansion. And this is this KKL work. I have to say that all my life until this point, KKL was reserved from a very famous work by Kankalai and Lineal, and now there is this new KKL, and okay, maybe there will be another one. Keren Kayemet L'Israel. Okay. That one predated even you. Okay. Okay, so now I want to say, okay, so we had that, and I think there was a time where it was already clear that something interesting is going on here in terms of local testability, and there was this question, it was kind of famous in some circles in computer science, is there a locally testable code that has constant rate and distance? And it seemed that these kinds of cocycles are candidates to be, they are locally testable by this KKL theorem, cocycles on the LSV complex, and can we get error correcting codes out of them? Now, the reason they are not already as they are good error correcting codes is because cocycles can be very tiny. They don't have large distance. Like a star is a good cocycle, and it has weight constant compared to the size of the complex. So you need to do something else to get locally testable codes. Okay. So this was the C3 question. We basically want to design some delta where care delta is the code. It has a local tester. And as I said, the small stars ruin this. Yeah, I only have 5 minutes, so what to do, okay. And the key is that there was this idea of the three-phase that said, if the triangles were the test, we had these 4 triangles that together must sum to 0. This is like a dependency on the constraints, and we want to imitate that. Okay, and then there were several works that did that. I won't have time to describe it too much. But just to say this. So we wanted to construct a code on this LSV complex and use this higher dimensional feature to devise constraints and also relations on the constraint. So, thank you, Tali. And thank you, Shai. No, maybe Shai is embarrassed. He doesn't want to give time to his own work, but okay, 5 minutes. So we were trying to do that and get some code on the, on this LSV complex. And we worked very hard, I think, but we didn't manage to do it. Instead, we came up with a different construction. I had to show it because it's on the T-shirt. So it's a different complex. It uses squares, and it's not simplicial. But
Is the picture due to you?
no. It's due to the graphic designer Barry, I forget his last name, from the Simons. He made this for us. So in some sense.
By proxy.
By proxy, yeah. So we understood how to define a code on this complex. Our idea was to take the Sipser-Spielmann expander code. It's a natural idea. I mean, I think it was going around. A lot of people were thinking about it. Instead of putting the bits on the edges, you put the bits on the triangles, and then for every edge, you put a constraint that says the triangles around the edge will satisfy, that their values are inside some local code. And then you use the fact that you have one more dimension, you have vertices, to say that now the different code words around the vertex are kind of related in themselves, and that will give you dependency among the constraints in a way similar to how we went from active triangle to a tetrahedron to another active triangle. We will move from some problematic code word to the entire vertex link to another problematic code word, and we will do a similar analysis. I'll show you in a minute. But what we weren't able to do is to show that we have a good code here that has constant rate and at the same time is locally testable. We needed these two components. Like in the previous work that I showed you, we had on every vertex locally a coboundary expander, and we had global spectral expansion. Similarly here, we need to have a code that locally is something like a coboundary expander, and that would make the proof go through. Maybe we didn't know this in this abstract level at the time, but we didn't manage to devise a code where we had both constant distance, constant rate, and locally testable at the links. Now, when I worked on preparing this talk a couple of days ago, I remembered the kind of thing we tried, and I remember how on the links of the Bruhat Tits building, these links are very specific. We know them, it's very easy to understand them. It's this lines versus points graph that I talked to you in the beginning. It's very easy, it's like on your hands. And it's very tempting to define various codes on this graph, but we didn't manage to prove local testability. So I thought, now I can ask AI. Because we had a code. It's actually very easy. On every point, you look at the edges touching this point and you say, I want this to be a Reed-Solomon code. And on every line, you do the same. And now can you prove that this code is locally testable? If you can prove that, then you can get something for a LSV complex. So I have some progress to report. The AI did manage to prove something for me that I didn't know, which I thought was pretty cool. But it still doesn't solve this problem like we wanted, so we are still headed to the squares complex. Okay, so we have this variant. Basically, we defined a complex using a Cayley graph. We have vertices for group elements, and we put a red edge for, right multiplication and a blue edge for left multiplication, and then you end up with these squares where you multiply from the right, and then the left, and then the right, and then the left. Maybe I did it the other way around. Sorry. And so you get this structure where the link of an edge, you have all these squares going this way, and the link of this kind of edge, you have squares going that way. And the link of a vertex really looks like a complete bipartite graph, which is great, because when you define a code on the squares, you put bit on the squares, then the code you get here is a tensor code, and it's already well known that tensor codes are locally testable. So we had this feature that on every vertex, the local code is locally testable, and then you need to prove that the global code is locally testable using the same local to global argument. So I'm sorry I'm rushing through this. This is the definition of the code. You have a group G, and you have generators A and B. You need this Cayley graph of G with A to be an expander, also with B. And then the code is just functions on these squares A, G, B, so that when you just fix an edge and just go over all the other squares, you belong to some local code. So here you belong to some local code, and here you belong to some local code. And then around the vertex, you're really belonging to this tensor code. So Okay, this is the definition of the code. And now, how do you prove local testability? So, distance and rate, it's immediate. I mean, once you know all these things, it follows very directly. And the hard thing to prove is local testability. And it's exactly modeled after the KKL proof. You start from alleged code word that satisfies almost all the local tests. So it has small rejection. And you do this flip algorithm. You kind of change F repeatedly to reduce the amount of rejection. Okay, again, I have this many weird thing. Okay, I'll zoom through this. So, let me skip this. I plan to say in a couple of slides how, more slowly, how it's really a very similar analysis. You have some random walk that is expanding, but it has some sticky sets, and you use the local testability to get out of the sticky sets. Okay, but okay. Let me just say maybe one more thing. The way our analysis ends up looking, we take a different point of view that is like a sheaf point of view, and this also was abstracted in work by First and Kaufman, where we look at every vertex and we look at what the vertex wants to be the correct local view around the vertex, and we do it separately for every vertex. So every vertex now sees a perfect local view, and we try to see if they agree or disagree. Okay, and then we analyze disagreement or disagreement. And this resembles kind of the third part of my talk, which I barely have time for, which is an agreement test, where different parts of the global function have different local opinions, and you have that they almost always agree. And you want to know whether or not this can be reconciled to a perfect code word altogether. Okay, and the same argument, not same, but very similar, was done by Panteleev and Kalachev for quantum LDPC codes and for quantum locally testable codes. And now let me say another 2 minutes on agreement testing. Okay, so this is agreement testing. You have some global object, think of a big simplicial complex, and you have small pieces. You can think of either links of vertices or maybe even just faces. And for every small piece, you have some local opinion, like this face has values for all of its vertices. And now you check if two faces kind of overlap, you check if they agree on their overlap or not. So initially in the PCP literature, this has been studied for a long time, maybe 30 years, I don't know. And usually people looked at the collection of all possible D sets inside a large N vertex set. So this is like the complete complex. And we had a whole literature of theorems about this, proving that local agreement implies global agreement. This is related to the parallel repetition theorem, so it was useful in PCPs. And it's very natural to ask if high-dimensional expanders also can give rise to such agreement tests, even though they're very sparse. So this is called de-randomized direct product tests, because it's a much, much sparser collection of sets. So with Tali, we managed to prove such a thing for any high-dimensional expander, but when the agreement was close to 1, like if 99% of the sets agree, only 1% of problems, you can deduce something. And notice that all the previous theorems that I showed you are similar. You say, if a little bit of problem exists, I can fix it. But the regime that was kind of interesting for PCPs was the 1% regime, where you know that only 1% of the sets agree and already you want to deduce something. And we conjectured that a similar thing should work. turns out that that was not quite correct, and there were obstructions. The obstructions are covers. Like if your complex has a 2 cover, you can get something that passes the agreement test with probability half. If it's a 3 cover, probability third, while being very far from any global function. So we realized when we were working on this with Roy Meshulam and later with Yotam Dickstein that really what you can prove if you have 1% agreement is that you have some cover where you have a global function on the cover. And this, to prove this, you needed to be able to move from something that's almost a cover to something that's honestly exactly a cover. And that's just another way to think about cocycle expansion. So again, cocycle expansion entered the picture, and we managed to prove this part. And then at some like faculty lunch at Weizmann, I mentioned to Alex that, you know, we have this, and do you know of any complexes that don't have small covers? And he's like, oh yeah, I have it right here. I just finished a paper with Michael Chapman, and you know, so that's how it was. And we just wrote a paper with Alex proving this 1% theorem, and also Bafna, Minzer, and Lifshitz proved the same theorem. And the next talk, which I hope you will also get the extra time that I stole from him, will show how this applies to PCPs. And sorry for taking too much of your time. Thank you. Happy birthday.
So we have time for 2 or 3 questions.
Are spectrum sequences hide somewhere in your construction of those folded squares?
I don't know. I wish I knew what spectral sequence is.
You used to compute shift cohomology, and you have some local things you test.
Fantastic! So we can talk after the talk. That's exactly what I love about this crowd. So let's talk afterwards.